Today is the 30th of March 2020. We are in class number 21. This is finite element method. And last time we almost finished up the mesh generator for the triangular elements. Actually, the part for the main finite element engine, which is the construction of the stiffness matrix and plugging in, actually already finished. If you want, you just move things around a little bit in order to get the code to work. The code will be uploaded, but I think I haven't done yet. Course material might not be there yet, but the video was completely uploaded since Thursday or Friday. Then we finish up the plane elements, and once we finish this class, then we are ready to move over to the other kind of element. Today we are going to talk about the reduced integration for quadrilateral element. Basically, this reduced integration is gonna make the R the R in the element code. Generally, you have Q4, right? You have the Q8, you have the Q9, and if you see all of these in the finite element program, that stands for the full integration element. And the full integration elements, for Q4, you have 2 integration points in each direction. Q8 and Q9, since if you look up to the order of the function, then you're gonna need the 3 integration points. Now, the point is that the issue is going to be like this. So we have the structural elements, and if we talk about the Q4, so we have the integration points located at the designated coordinates C and eta. And when the element deform, especially when you talk about the case where we are interested in the shear behavior, you might end up with this picture. And this picture here, by the way, I just figure out why I was so slow in the last week. Since it is the work from home and teach from home, so I didn't have the coffee with me close to my hands, and then I forgot that this is my ritual to have coffee in the morning. Generally, I don't have coffee over weekends in my house, so I don't have one. And then the teaching was slow because I didn't have coffee, but now today I had coffee. So I think that might enhance the situation, enhance the mood of the class teaching. So you might feel better because my voice will be more lively, and speed will be, well, of course, a little faster than normal. Okay, so this is identical to the case where when you deal with in the beam, and at that point we talked about this issue in Timoshenko beam, which is let's take a look at this issue. So the structural elements originally look like this. You have if you have 4 nodes, then you have 4 integration points in total. I should draw the node a little bit to make sure that we are understanding that we let's say the 4 node is a full integration. this is the full integration for Q4. And then when this member is subjected to shear deformation, deformed by shear, or let's say distorted. So when the element is distorted, you hear helicopter sound. Oh, seriously? Anybody else hear the helicopter sound like milk? So I can adjust the setting. I guess, well, let me try. I don't hear anything, milk. Is that you alone, or is it happening with others? For that helicopter sound milk mentioned, I wonder. I just listen to the YouTube live, and I don't hear anything but my voice. Is that like your PC, maybe the connectivity or so? You hear Milk, Navindra doesn't hear anything, so probably your system then. How about others? Any others hear this sort of thing? The noise, any disturbance? Because over here, I think, okay, if you hear the bird sound, that is, yeah. So John is okay, Navindra is okay. Milk, you check your system then. Okay. So let me continue. Thank you guys for the input. Okay. Now the element is distorted under the shear, and as I used to teach you in the Timoshenko beam, when we set up the integration point, which is like at the designated coordinates. In fact, this piece of element subjected to the shear, which is not as large when you measure the shear at this location, because at this location you're gonna see like the shear or the distortion is about this is the distortion. Yeah. I clear this out. So these two are the distortion, the angle of distortion, but actually if you average up the elements, then it is just here, and the distortion is not much right at the middle. So you do it this way. If you, the more you get closer to the side, the more you are having the shear distortion evaluated at the integration point. And from that, you remember that I recommend you two approaches. So the first approach, you to alleviate the shear locking issue. Okay, so we can first do the, well, use fine mesh That's the first option. The second option is to use the reduce integration. Use the reduce integration. Okay, so two approaches. We can see that fine mesh helps because the finer the mesh is, the exaggeration of the shear will be less and less. So I will just redraw this picture. Oops. Okay. This one, if okay, we look at these two. So the first one is just the one single element. So this is the coarse mesh, and the next one is the fine mesh. Due to the nature of discretization, we will end up with the over estimation of the shear strain. So this one, I'm gonna mesh it down this way. Okay, and if I mesh it further, and here further, and okay, and there, and here. Okay, so from here, these two pictures, I will draw the coordinates a little bit, the local coordinates, and I can compare with this one. Okay. So in the way it looks like coordinate local coordinate place in the global one, and then I identify the integration point. So you can see very clearly here that the angle, right, in these two sides, they are actually different. Yeah? So it used to be here, and then it goes this way, and it used to be here, and it goes like this. Okay. Whereas for this one, relatively to okay, so they are not going to the opposite side like before. So the change of the angle or the distortion measured from these two system of discretization, you will find that the shear deformation will be more realistic than the previous one. more realistic shear, basically shear strain, whereas this case it exaggerates. I think exaggerate, we have 2G, right? Exaggerate. Shear deformation or shear strain. So the first countermeasure is to use the good discretization. Of course, good discretization of fine mesh is always improve the finite element solution, because your physics will be your numerical model will be more and more closer to the real physics. So that always the case that you get a nice improvement from the fine mesh. And another issue, another possibility is to use the reduced integration. That could be used as well. So to use reduced integration, you will, let's say, evaluate the shear distortion in the using the fewer integration points. So for Q4, if you use the reduced integration point, you will find this Q4R in your finite element software. Q8R and Q9R. So this is going to be 2 by 2 Gauss points. Instead of using the 9 integration points, then you use 4. And this turns out to be 1 by 1. Now, let's look at this issue. The reduced integration is to be performed in shear mode only. You have nothing to do with the other modes. So if you think of the rigidity matrix D, that comprises 2 major parts, the volumetric part and deviatoric part. Volumetric part, we talked about the change of volume, and the other part is the shear part. Basically, previously the D comprises both things, but now we are trying to break it down into 2 components separately, because the treatment we are going to perform is going to be carried out in differently in these 2 modes. So the D is right now represented by the D volumetric plus the D deviatoric. And when you consider the stiffness calculation, the K is equal to integration of the B transpose D and B, okay, and over this domain. So the same thing is going to be like this: the volumetric plus the deviatoric part, the omega. Okay, and then we break this thing down into 2 parts like the beam. This one is the volumetric, this one, next one is the deviatoric. The full integration will be performed over here. You cannot reduce integration this part. And the next one is the reduce integration. So reduce integration will be carried out in the shear element, in the shear part only. Now, it sounds cheaper, right? It sounds like it is cheaper. You feel like, hey, if it is the reduced integration, that means the number of integration points will be less than the full, the normal elements, and so the operation will be less, because, for example, if you are dealing with the Q8 or Q9, it used to take 9 operations to evaluate the B matrix, and then you calculate B transpose DB, and then you accumulate that value in, so you have some sort of sum of the B transpose DB weight in C, weight in eta direction. So you feel like, oh, if I use Q8R, that means the operation will be reduced, but you are wrong. It's not actually reducing. Why? Because if you look at this, you can see that the operation is actually increasing. So if you used to have 9 operations before for a Q8 and Q9, now you have 9 and then you have 4. So the volumetric part will be evaluated separately from the deviatoric part. So you end up with 9 plus 4, you get 13. But what you have is the improvement in the behavior under the shear mode. So, well, essentially we are going to execute the code and see how this, what might be the concern we have from this sort of reduced integration element for the quadrilateral type element. And then we will talk about the issue over here. So the element, reduced integration element, was actually developed. The issue that will come after the after the use of reduced integration is the spurious mode. This is the terminology for you to understand when you use the finite element analysis. This spurious mode is corresponding to the mode of deformation that modes of deformation that cause zero strain or zero energy. Well, sometimes we call it zero energy mode. What could be included in this zero energy mode? First, rigid body. Rigid body modes. That includes, first, rigid body translation. And rigid body rotation. So, for example, you have the element like this. You could have the rigid body modes that brings your element to here, or also upward to there. So rigid body in X translation and Y translation, these are possible. So it can move if you don't put the boundary condition properly. Well, that's why you need the support. Without the support, then it's gonna fly, right? You can try. It will turns out that you can solve the matrix, but as you solve, you will see that you have the solution which is not unique, because it could be like anywhere. The object could fly up, down, left, right, and also can rotate. Oops, it doesn't look like the rectangular square. Okay. Okay. So you can have the rotation and translation, whichever. Okay. So that's the first thing. If you secure your element by putting just one hinge at one corner like this, and you run the analysis, well, you can see that the boundary condition is not going to make the element stable. Thus, you will find that this body can rotate, but it will not translate because you lock it against the X and Y rigid body translation. Okay, so these are the possible rigid body modes which cost you zero energy. Energy means the strain energy, to be precise. Energy which is caused by strain. So that's the first thing. The second thing, we also have the zero energy mode, that you might find the change of the shape of the element. For the rigid body, you find that the element is just identical to the element before the analysis, so identical to original configuration. But the matter of fact is that the element is not staying at the place it used to be before. It rotates, it translates, but there is no change in the geometry. So that's the word rigid body comes in, because rigid body refer to no change of geometry. It used to be square shape. It ends up to be the square shape. Okay, so it doesn't really change the thing. The second one, not only the rigid body modes, we have the so-called spurious mode. Not spurious mode, hourglassing. Hourglassing modes. The hourglassing modes, you have the change of the geometry. So I say that geometric change is possible. So it is possible to have the geometric change, but this geometric change is causing no energy. So basically, no strain. How does it look like? The mode like this could be this shape. This is the hourglass shape. So at the integration point, you may have so in some configuration that finally the energy turns out to be 0. So what is the problem? As it has no energy or require I should just say precisely that it requires no energy to deform to this pattern. Okay. Now, how do we detect or how do we come up with these modes? So look at the concept of the zero energy mode. Zero energy mode is actually the mode that the sets of deformation, right, that is coming up, and it does not need any energy, or basically that's contribute to the force, right? So if you have the stiffness matrix of one element, this is just one element only. Generally, we construct the stiffness matrix. You have the K times U equal to external force. The point is that we are worried that the some mode like this, it does not need any external force to deform. So when you solve the system of equation, you get like the jackpot added on top of your solution. Your solution wouldn't supposed to have this zero energy mode, but now you get it for free, and you don't like this sort of freebie. So let's we have this set up, and I continue to somewhere over here. Okay. So as I mentioned, if I have the zero force applied to the system, that will refer to zero energy, right? Zero force applied. how do we get the zero energy mode? Well, you have two possibilities. First possibility, if your U is the vector of 0, this is going to give you the trivial solution. That means we don't have to do anything. If U is equal to 0, you have 0 energy, and then go to bed. It does not give us or enrich us any idea. So the part that we will get some information is going to be from this one here. Okay. So if U is non-zero, we don't need the 0 U. So if U is not a 0 vector, the determinant of K must be 0 to satisfy the condition K U equals to 0. Okay. So we are dealing with eigenvalue problem. So we can construct the stiffness matrix of an individual element in in Octave or Matlab, right? And then you'll be able to find the eigenvector and eigenvalues. Okay, so eigenvectors will be taken, and that will be the sets of deformation to be added on top of your element in order to see the shape that costs no energy. Okay, so the derivation should be just up to this point here. Okay, the work done in iPad will be up to here. Then we will switch to the computer screen and we'll be working on the input and output of the program a little bit. So let me switch to the desktop screen. Right. Now we are getting into the desktop screen. Let me move my iPad around a little bit. I'm gonna need a studio for too many equipments around. I cannot see the mouse. So we are right now in the screen, and first of all, I think I'm gonna need to change the input and output. I need the program to read the information from the file. So the rectangular mesh subroutine over here is going to give out the file, the input file. Okay, and the input file will include the XY core and Nmap. And later on, when you jump into the main program is gonna read the XY core and Nmap and store in the variable. So the procedures here will not be executed anymore, so it will not take time. Basically we just need these two. Okay, and we can come all the way down to the bottom, because right now we have all the mesh plotting. Actually we have all element type 4, 8, Last time we made the mesh for the okay, I get it. We made the mesh for the rect mesh. Okay, we should. Oops, why is it going like this? Fine. I think I just. Why does it add the space for me? Format. Indent code. No. Format. How to convert line ending. Why is it there? I never added space. What is that? Delete to start of word. What? Delete to start of word? No. That's not what I mean. Huh. Why is it adding like a space to... Oh, it come back. Okay. It comes back. No more space. Okay. So this one start from the element type number 3. It has everything. And then at the end, I think I need to write everything into the file. Write the input file. In the commercial computer software for finite element analysis, they do it this way, identical way. So the input file will be written separately. When you do the finite element problem for in the software platform, you construct. You're gonna have the CAD part first. You're gonna construct the 3D elements. So you put geometry in, you mesh it up, you mesh, put the condition for the mesh for each zone. It depends on the result you wish to see and the quality of the result that you might emphasize in some particular area. So the mesh will be generated according to your need. And you end up with the sets of geometry, mesh, and coordinates of the problem you wish to analyze. And then, before you run the analysis, you got to have to write the input file. Right? So write the input file. It is identical to here, what we are doing. We are going to write the input file. Previously, we didn't, because this is just a little small program for the finite element learning. So I didn't make the input file writing at the beginning, but now as it gets bigger and bigger, we might consider doing that. Write an input file. Sorry sir, can you zoom in a little bit? Thank you. Okay. Better? Okay, yeah. Write an input file. Thank you. If you have anything, then let me know so I can help fix that for you on time. So to write an input file, you need to look at the syntax for writing the text file in Matlab. So here it should work as well in the Octave. So you search for the input file writing and then you end up with fprintf. For fprintf, you look up for the like this one. This looks like what we need to do. So first of all, you can see they initialize the values of the array x and a, right? And then file ID has to be fopen something, some name, and w. W means we're gonna write into this file. So at the very beginning, I think we need another input FNM, which stands for the file name, and I delete this part here. So FNM is going to be used over here. File ID equals to file open. You don't need to memorize everything. We're gonna die if Google is not there. So file ID is equals to fopen, and then we don't need to the code FNM, and then W lowercase close, and that's it. File ID is identified, then print F file ID. I think I will need just the first part in the bracket. Well, 1 second. Talking too much just irritate my throat. I don't cough for a couple of days without the class, and then once I launch the class another time on Monday, then I end up with the irritated throat. Okay, print F equals to file ID. So you just put something there like the XY coordinate. XY coordinates. That's it. I think the syntax looks good. Close the bracket. After this, we are having the F print F. F. Okay. File ID, and you start with sort of X and Y. We're gonna make it look better later. And now for I equals to 1 to how many? Size, right, of the XY core. The size we gonna go is the number of the nodes we have, which is the first index, which is the row. So we take the size of XY coordinate matrix in, well, row and column. So the comma 1 means we're gonna take the number of row. The number of row we have is the number of the nodes we have in total. If you go for a comma 2, you will end up with just 2, because the XY core is the NNDE by 2, as we have just 2 coordinates, X and Y. And next, we're gonna print F into the file ID. What do we need to print? When we print something, we have to convert it into the string, like this. Let me check. File ID %6s 12 blah blah. That's for the exponential of the x. Okay, we don't care about this. And 12.8. 8 means 1, 2, 3, 4, 5. Oh, 1. Sorry. 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 decimal place. Right. 12 means the starting. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so okay, there's still some space before. So okay, I get it. Now we have the syntax, and that's the A. So the A is the X and that thing. Okay. Oh, so this is pretty easy. Then we don't need the for loop then. Well, let's try. If it is going to be that simple, that's gonna be nice. We don't need even the loop. So percent 6. Do we need just 6? Yeah, make it 10 point. How many decimal place we need? 0.8, and then space and percent, and make it 10 is the first one, and 0.8. Well, we don't need that many. Yes, 6 is good. 6.8 and 12. Could it be just 12? 6 mean the 6 and then plus 8. 6, 7 for the dot, and then 8 is 15. So the next one is 20. Okay, 0.8. And all this has to be enclosed inside this quote and comma and xy code. So I think I follow the syntax. Then I just save it and check another time. Okay, rect match, and then I will call this well, what how did I name it? Oh, FNM will be there. So I copied everything. No. Okay. RECMEH rect match element type, which is add and x, make it 4, and y, make it 5, hx2, hy2, and file name test1.txt. That's it. Close it and hit and bug or not. Oh, why it takes so much time? It was supposed to take this much time. Oh no. Okay, I know it. It takes so much time because of this. This is on the other window. It is plotting this out. Waste our time. Come back here. Label, make it 0. The label part is just the time consuming part. So when it plots out, it takes so much time. Let me execute. Well, bye. It is almost, yeah, almost there already. So let it run. Or should I Control C? Control C. Oh, yeah. If you want to kill the process, just Control and C, then it stops. So we don't need to wait until this finish up that plotting. Okay, I just disable the node number plotting because we don't really want to know that. Okay, invalid format specify line 214 column 1 always. Bug is a part of our life. Okay, so it gives a complaint. Let's take a look at this. No, it is not giving out anything. Line 214. Where's it? Rect match line 214 column 1. Maybe just disable it. We should have the F close, F and M. I think this is just to make a, well, It's just strange. Something strange that works. I don't like it. I think I need to get a better idea how it works. Okay, then I can remove this. And the next one is going to be fprintf of what nmap. And we have this fprintf and home, copy and paste. We're gonna have what is going to be this one, make it 5s. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 10. Okay, node number, we are not going to handle more than hundreds, right? So 1, 2, 3, 4, 5. Okay, 1, 2, 3. No. 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So this is for Q8. We can try it for this one here first, and then the next line fprintf of the file ID. The definition for that code is like that, sir. Thank you. Your text file printing is done column wise as per definition instead of. So it said somewhere in that help. I didn't read that. Okay, thanks, guy. Good. Thanks for your collaboration. So let's look at this next. It's gotta be the transpose again of that /r/n. So why did they make it not consistent with the shape of the matrix we see? Transpose of the nmap, right? And then nmap, close the bracket, close it, and this one integer format. Let me see. Let me check integer. Is there any integer? D. Okay, yeah, the %d is going to put the round up, right? The round. Okay, %d in the format spec inputs the points each value in the vector around the A. Okay, the %d, and I need probably the 5% d4. This is 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. Save it and test it. Check into editor, revise. Okay, XY core is there, nmap for the node number 1, 2, 3, 4, 5, 6, 7, 8. But why do we have this many? Okay, we bump into another jackpot. We don't need that many. We need just a few. 2 and 3 discretization in the vertical direction to make it fast. Yes, reload please. And then okay, 190 something nmap. It is not right again. So we gotta check it out again. Transpose of nmap. Draw the nmap. So what is our nmap for this case? 1, 2, yes. 1, 3, 11, 9. It does not look right at all. Well, the first one, this one is correct as it should be. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4. Okay. Well, the second line here, D, like this, it does not give the space at all. Let me check back again into this. %D, control file, % and D, and we have %D and okay. %D integer and sign base 10. Floating number, we don't use it. Character or string C and S. Okay. %D or %I base 10. Fine. With I did it. It is 5D, not D5. And okay. And it doesn't report the error. That's a bad thing. No. That's it. Save it and test it. Slow. Oh boy, yes, right. 1, 3, 11, 9, 2, 7, 10, 6. Okay. 3, 5, 13, 11. Okay. But now this is lacking a little bit. Let me fix it. So this is what? 1, 2, 3, 4, 5. So in there is like 4. Okay. So it just picks up the first one only. Is that so? Okay. Then I make it 4D. And make it %1S first and %4D. So I have this space first. We'll see if this is going to be fixed. Yes, please. Okay. So what? That is the one. Come back. What is supposed to be just right behind 5D, and A, and then it goes like this. So I did it properly previously. Actually this is the same, right? So 5D, I did it 5 and then 4, 4, 4, and then it turns out to give me all 5D. 4D. If I do it this way, 5D, percent D instead of, oh, okay, I fixed that. Okay, thank you. Save it. Oh gosh, 1, 3, and then 11. Fine, I can make use of it a little bit. 1, 2, 3, 4, 5. 1, 2, 3, 4. No, 5. Okay, I think it has to be done this way. Then 3D. Let me try. 1, 2, 3, 4, 5, 6, 7, 8. Please. Okay. I got it. So it just took it moved the cursor to the back, and then 1, 2, 3 like this. Well, okay. So right now node number, then I will delete the space. Node number 1, 2, 3, 1, 2, 3, then add 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 5 will be replaced by 8, and save and execute. And then we're gonna do the read, but the read should be easier. No number, okay, it doesn't, it needs some more. 1, 2, 3, 4, 5, add 5 more, so it turns out to be 13. Save it and call it. Oh boy, yes, an end map. I don't need it to be there. I need the leftmost, so end map. Well, actually this might be the trouble when we read, but we'll see. We adjust the format a little bit. I think the read should be semi-automatic. It might discard the space before the figure. So end map is just 4. I give it just 4. Okay, and the other things, 0.8. Can I make it 0.10 and make it 14, 28.10 xy coordinates up there. So x will be 14, and y will be 14 as well. Let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It will be just lacking a little bit, and we will do the fine tuning and finish this up. So what is it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14. Okay. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Why is it? Okay. This is row number 45, 44. This is 32, 31, 28 is here. Why is it coming out this far? the column 15 is there, X and Y. Y was supposed to be a little bit away, and then okay, 14 is counted from the back over there. But yes, okay, now yeah, it works. 1 2 1 2 3, and that's it. 1 2 3. Only X and then delete Y back. 1 2 3. Okay, I think we get it now. It should be ideal for now. Too much. Okay, X, Y, align, end map. Okay, so due to the given data structure pretty much like this, we are going to come down to the main code in order to so we use the rect mesh. We have the file name stored in test1, and which main update, no? The main update over here. Format intent code. Oh no. Why is the code that thing? I think the command delete to end. No. I don't know what's going on. The code just give me some special convert line ending to Windows. No. Delete line, delete duplicate. Well, fine. Just waste my time. Geometry, we don't need to talk about this anymore over here. What? Format unindent. Okay. It looks normal now. Element type, do we need to specify? Basically this rect mesh over here, this is we need to make it if e type is equal to 3, then you have this, and then no, XY code doesn't need to be printed out anymore. Else, if the element type is equal to 4, then the print is going to be different. This is specific to the element type. And then copy for the 8 and for the 9. This is good already for the 8 and if. So we have 4, we have 8, and we have 9. And this is good for all. For a 3, then you don't have that many node numbers. You got to delete it out. And yeah, like this, 1 2 3. So it is removed this way. 4, of course, removed, and like that before. 1 2 3 4, right? 13 and many 3s. Number 8, no change. Number 9, just a little add in. 1, 2, 3, 4. 1, 2, 3, 4. And one more percent 3D. Okay, that's it. Well, so this will accommodate all kinds of elements. Again, this code is made to handle just one kind of element. We can make it handle more than one kind of element, of course, but that's just the administrative coding, and it is just the time consuming part. We can have like a separate session, like another class, if I have mood. And many times I said if I have mood, then the mood never comes. well, if it comes in. And okay, so the element, actually you can specify 4, 8, 9, and it could be 4R, 8R, and 9R. So if we have the reduced integration elements, then the procedure could be different. We can have like T3, Q4, Q8, Q9, and Q4R, Q8R, and Q9R. In total, we could end up with 7 kind of plane elements, either plane stress or plane strain, but that could be in total 7 kinds. And we can make all of that, we can include all of that, but the class will be more like the graphic user interface and the administration coding more. Okay, so over here element types, I think the key thing, the key thing is going to be this part here, FNM, the file name, because we're gonna read from this file name, right? And if we are going to read from this file name, then we're gonna make a function input read FNM from the file name. So we're gonna read the input. We're gonna read the input, and I'm not going to well, I'm not going to let me bring up the file from before. I don't remember anything. So from the frame analysis, I think, yeah, read frames. I will open this one with Octet ไม่ได้ Okay, WordPad. I don't want to switch the directory. So okay, function. This is what read frame description from the input file. We make the function this way. Editor, make it smaller. We're gonna return NELE. Well, first of all, NNDE, NELE, number of element, XY code, and Nmap. We could have some other things, element type. Again, this one might be the vector or the matrix in the future. And the next, FID equals to fopen FNM, and then we read the first of all The test over here, actually we should name it description. We should write the description like the date on version, file name open, and then the fprint description, which is given by this. Okay, at least we have the file description. We know the worst thing to do is like a file name. So write down the file name into the header of the file, at least. So if skip line, how many lines do we need to skip? 1 line, 2 line, and the file name. So we have 3 lines to skip. We can add more if we have more information put over here, like versions, the date, the time, etc. And then if get line, the FID and node equals to this dummy. Okay. Get XY coordinate. So we take from here. We don't get any numbers, right? So we replace this one here. So we initialize XY coordinate equals to okay, we have to append. First of all, we do not have the size of XY coordinate. As we do not have the size of XY coordinate, we have to read and append the array. Do you understand what I mean? We cannot do the cheating. The cheating means like I got to put the number of element and number of node over here in the input of INP read. And if I have to do that, that means the code is not quite automatic, because I gonna have to figure out all the parameters. So or I have to put these numbers of X coordinates and number of nodes in this file, and number of elements in the very same file. Oh, that is possible. Easier than appending the number or the array in. It is not that difficult though. So we're gonna print we have the file name already, right? We print the information of the number of nodes. It was supposed to be just 4s, and then n home, copy, paste, and here is the NNDE, but instead of 4s, it is 4D. N, copy and paste. So NELE, number of elements. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and number of elements, it would be enough. Number of nodes, it does not count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Seriously, 15? Okay. There it is. Number of nodes is in number of element, and ELE must be in. Save it and execute it. So we get the revise. Oops, it seems like has been modified. Okay, but it has a undefined. Number of node is undefined. Who cares? Undefined. Fine. Size of xy core, comma 1. NELE, who cares? Size of nmap, comma 1. Without these two, still we can obtain. Okay. Now test1.text file name is there, number of node is given, number of element is also given, and then number of node is going from the 8 to the 36, okay, which is 29. Elements is 1, 2, 3, 4, 5, 6, which is correct. Now we read it. So the data structure looks like this one, 3. So we skip 3, 3 or 2, 1, 2, skip 2, and then we go to the number 3. So I comment this out first to make sure that we comment, format, commenting, comma 3, and then dummy equals to fgetLine, and then first thing was node number, right? NNDE is equal to string to num of dummy, and then just keep it this way because I really want to what is the name? Input read. So I keep it this way, and then okay. So if I call this program INP input read, the input file name is test1.text, test1.txt. End node turns out to be 0 by 0 because it should be just to save it and do it again. Okay, nice. So we need to skip just 2 lines. Skip 2 lines, and then we come to here, and then we skip another line, and that's supposed to be just 1, and then we dummy, and we get the NELE. Okay, and we are done with that. We get number of element, number of this. Okay, we skip 2 in order to start reading the xy coordinates. The xy co is equal to zeros. How many? NNDE, comma 2. And nmap is equal to zeros. NELE, comma, well, we need the element type as well, right? So you get file name, you will need the element type. Otherwise, we're not going to be able to allocate the element type. One, two, three, four, five, 6, 7, 8, 9, 10, 11, 12. So we need to allocate the size of the Nmap, and without knowing the element type, you cannot. Okay, yes. Again, got to do it again also to make it appear. Okay. Oh boy. So the element type 8 is coming in over here. Then I need to insert the, what time is it? 10:16. If our Professor in class, is it like a video taped or is it a live? I think he prefer video taping because he need the full picture of himself with the actions in front of the screen. So but I think as we are not encouraged to go to the campus these days, then he needs to do it from his Microsoft Surface, and he won't be able to pre-record the video. Fine. Where? EndNote. Okay. So we have this element type, right? E type. Oops. No. DMMY is correct. We need the element type. Oh, yep. And then Nmap, comma, ETYP is allocated. Let us save this one and see the InSpread input rate. Where's the NELE? NELE. First thing first. Element type first, element type 2, and then get this. So element type has to be read out, and then and then F skip line 1 and F get line, and then you get the EndNote, and then you F skip line. Okay, so this is going to read things well. Element type 8, the number of elements, we have 26 elements, and the total number of elements 29. We have number of nodes is 29, number of elements is 6, and element type is Q8. Right, so right now we transfer all the data from the input file back into the parameters over here. We're gonna feed all of this, but we need to read this first, the X and Y coordinates and the Nmap. So let me just take this part. Well, 10:19 already. I think I have some, okay, this part can be used, so I copy this from here. Now we get the number of nodes. Let's see. We have 2 rows, right? So we will F skip line. Where is it? I think I'm getting older. The eyes. Oh, okay, F skip line is there already. XY coordinate is already allocated. Nmap is already allocated. So we're gonna do the I equals to 1 to NNDE, okay, which is perfect. Dummy, we get line and FID, and then string to num of dummy, and then we get X and Y coordinate accordingly, alright? And let me write down XY coordinates. And later on, I gonna transfer the data from input file. So we have mmap and the node number. We got to clear off these two rows. So it is unused. It is just the interface. And then we can use this part here. For I equals to NNDE to NELE. Okay. And then we get the mapping of the nodal points. So that is going to be the Nmap. Okay. And then finally, I will be able to plot the Nmap right here. I save it and then I call this subroutine. Okay. We don't have much time. Gonna have just a few minutes break before the earthquake engineering. Okay, we'll see. Let's see. So everything was read correctly. Element number 29 from the total node and up 8 to XY coordinates is taken 4, 6, 3. Okay, everything is perfect. And the Nmap, the mapping 1, 3, 11, 9, 2. Okay, if we call the reg match for another time and we check this, save it, and reg match. We want to check the, okay, reg match. Let us see the plot. Okay. Too slow. Yeah. I didn't delete the old plot, so this is actually not there. I didn't close the window. So for those nodes that is coming along with the figures only real. Sorry, I didn't clean this part off. Okay, so we can look at this element number, node number 0, 0, 1, 0. 2, 0, number 4, 3, okay, everything looks perfect. 0, 1 for this, and then 2, 1, and then 4, 1, okay, so perfect. Nmap, these are the numbers we obtained from the reading of the data file. So 1, 3, 11, 9, 2, 7, 10, 6, right, this is for our Q8 protocol. 3, 5, 13, 11, 4, 8, 12, and 7. Okay, I think let's look at the last one. 19, 21, 29, 27, 20, 24, 28, and 23. Okay, perfect. Okay, so we have the input file there, but we cannot make it to the to find the eigenvector of our element, so we're gonna keep this for the next class, and you have just 7 minutes before the earthquake engineering class time. Right, see you on Thursday. Bye bye. Thanks for watching.